In this section, we're going to be defining derivatives for both exponential as well as logarithmic functions. We're going to start with the exponential functions. So if you'll kindly recall, an exponential function takes the form f of x is equal to b raised to the x power, where b is referred to as the base of the exponential. The rules for b are that b had to be greater than 1 or between 0 and 1. Now, if b is greater than 1, we have what's known as an exponential growth function, and if b is between 0 and 1, we have an exponential decay function. So what we're going to do to derive this derivative shortcut is go back to the definition of a derivative and say that f prime of x is going to be equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. Now, in the context of our function that we're currently working with, this would be b raised to the x plus h power minus b raised to the x power all over h. Now, there's a property of exponents that says when exponents are added, I can split this up into two bases that are multiplied together. This property is more commonly used to create one exponential from 2 rather than to create two exponentials from 1, but you'll see why it's important in just a moment. The reason that it's important is because there is now a greatest common factor in the numerator. And the greatest common factor that we have in the numerator is b raised to the x power. Probably didn't need that set of parentheses. You know what? I regret nothing. Now, the important thing is the limit that we're dealing with is the limit as h approaches 0. So everything that's inside here perceives h as the variable in question. Neither b nor x counts as a variable. So using the constant multiple limit law, I can pull that b raised to the x power outside of the limit. Say that this will be the limit as h approaches 0 of b raised to the h power minus 1 all over h. Now, what I'm going to do is set up several different values for b and see if we can figure out what this limit is going to be equal to. So I'm going to try this out with b equals 2, b equals 3, b equals 5, and b equals 7. That'll be the limit as h approaches 0 of 2 raised to the h power minus 1 all over h. The limit as h approaches 0 of 3 raised to the h power minus 1 all over h. The limit as h approaches 0 of 5 to the h power minus 1 all over h. And finally, the limit as h approaches 0 of 7 raised to the h power minus 1 all over h. In all of these cases, direct substitution property is going to yield 0 over 0 as it typically does. So what I'm going to do is demonstrate on the calculator how we can come up with a reasonable approximation for all of these. And we're going to try to do all of them at the same time. So if you need to pause right now to grab your graphing calculator, that would be a fantastic idea. So with that in mind, we have parentheses 2 raised to the power of x minus 1 all over x. The calculator will only deal with x's. It won't let me necessarily do an h in here. Well, it will. It'll just make the process a lot more long and complicated. So I'm just going to hit the variable button and use whatever variable it has for us. In this case, that would be x. What's great about the graphing calculator is its ability to do so many of these at the same time, save us a little bit of time. So with that in mind, here's what we currently have. I am going to go to my table settings. I'm going to clear out all of the data that I currently have in here. And we are looking to take the limit as h approaches 0. So I'm going to select several different positive values to plug in. As well as several negative values to plug in the opposite order. Hopefully everybody can see that we are aiming for the number that is between the 4th and 5th line on each of these. So for the first column, that was for 2. That's about 0.6931 or 2. So about 0.6931 or so. For the second one, looks like about 1.0987. For the third one, looks like about 1.609, we'll call it 5. That's close enough. 1.6095. And finally, about 1.94, we'll call it 59. 1.9459. Now, my guess is that regardless of how long you've been working with math, you don't necessarily recognize any of these numbers. I certainly didn't the first time. But then, if I raise e to each of these powers, something pretty magical happens. So this is for the 0.6931. Turns out that that number is about 2, which means that the original number would be the anti-exponential of 2, also known as the natural log of 2. Do it again with our second number, 1.0987. We see that the result is about 3. Turns out that this number was actually the natural log of 3, not 5. 3, sir. 3. This one is about the natural log of 5, and this one is about the natural log of 7. Now, I'm hoping everybody is making the connection with the fact that whatever the base was, this limit is equal to the natural log of whatever that base is, letting us know that the derivative of an exponential is going to be the same exponential times the natural logarithm of whatever the base was. So this is the derivative with respect to x of the exponential b raised to the x power. That also means that we have one very, very special case, which is the natural exponential. If I take the derivative of e raised to the x power, I am going to get e raised to the x power times the natural log of e. However, the natural log of e is equal to 1. So the derivative of e to the x is going to be e to the x. This is going to bring me to my favorite joke to tell throughout the course of the semester. I will pose the question, what is the derivative of e to the x? And you will respond, e to the x. And I will say, no, what's the derivative of that? And everybody will laugh and die a little on the inside, as you are forced to laugh at my jokes.